Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to do this briefly. This is Dan. He works at Princeton. He does a PhD. And he's going to talk to us about hardware verification. So enjoy.
Hello, can everyone hear me? Okay, great. So thanks for having me. It's great to be here. As Jod said, I'm a PhD student at Princeton, final year PhD student. My area is broadly in computer architecture, and today I'm going to talk about my thesis work in specifying and verifying memory consistency models. I want to start with some very high-level overview, and then I'll work my way towards why consistency is important, why we need to be more careful about specifying it, and then what my approach is to verifying it. So this slide is nothing new. We know everything is multi-core. That's not going to surprise anybody here. The only thing I really want to say is that this is really true across the spectrum, from supercomputers and data centers all the way down to mobile phones nowadays even have 4 or 8 cores in them. So really, memory consistency is becoming a thing that really applies across the entire spectrum of computing, and we have to make sure that the consistency models that we use and build actually reflect that fact. And in particular, I mention mobile devices not only because they are multi-core, but in fact, they're much more than that. They actually are heterogeneous nowadays. They're very heterogeneous, and even more and more so with every generation that comes along. So if you look at it, a typical mobile chip nowadays, it looks something like this, where you might have CPUs, and that's what you would normally think of for memory consistency models. But really, that's just a small piece of the chip up in the corner there. Chip nowadays would have GPUs and accelerators and digital signal processors and all kinds of things that haven't in the past been considered in the same way relating to memory consistency models, but now they have to. As they become more and more programmable, we have to make sure that they also get included into that space as well, because they're all communicating via shared memory. So from an architect's point of view, the picture might look something like this, complete with architecture-style cartoon diagrams and everything. But really the point is that these things, they don't just all live on the chip, but they all communicate via shared memory. And in particular, nowadays, everything is converging towards shared virtual memory, so it becomes easier to share things like pointers and data structures with pointers back and forth without having to do all kinds of translation back and forth the way it used to be for CPU, GPU a few years ago when it first got started. Now everything is converging towards this shared virtual memory paradigm. And that's true even sometimes when the physical memory space is more complicated. So even if you think of, say, NVIDIA discrete GPUs, for example, they might still have a physically separate piece of memory for the GPU and the CPU, but even then they tend to share the virtual memory space for exactly those same reasons. So that's all important. That's good. We know we need to build consistency models to address things like this. But then the last piece of it is that it's not just about building and designing these systems. We also have to verify that they work correctly and don't have any bugs in them. And unfortunately, that's a very difficult thing to do. And as you can see behind me, there's been some bugs that have appeared in the memory systems with somewhat regularity. So there's been, a few years ago, there was a bug in the AMD TLBs that affected the way memory translation was taking place. And then just a couple of months ago now, Intel released the fact that they had a bug in their implementation of transactional memory. And so their solution for that, at least for the chips that had been sent out so far, was to just simply disable it and say you can't rely on it. It might have a bug, at least in some corner cases. And so the only safe thing to do is to just turn it off. And so that's pretty unfortunate. That's not really what you want. You want your features that you're advertising to work. And so what this means to me is that we need to have some more intelligent way to go about verifying that these features, memory consistency, transactional memory, and so on, are implemented correctly at a microarchitecture level. So the typical approaches that are used in terms of testing and just brute force testing to make sure that you don't see any illegal outcomes appearing, that is great, but it's very expensive and it's not as intelligent as it maybe could be. So that's what my main topic is going to be today will be about how to do this microarchitecture level verification at a more intelligent way. Okay, so this is the overview of my talk. Today I'm going to focus mostly on the first project here. It's called PipeCheck. And that is the project to specify and then verify memory consistency behavior at a microarchitectural level as opposed to an architecture level, and then compare the architecture and microarchitecture to each other and make sure that the microarchitecture is correct. And then at the end, I'm going to talk very briefly about a follow-on project called Armor, which would be more about, back up to the architecture level, how to specify things, and then beyond that, how to translate between memory models. If I have, say, the example of ARM processor, mobile phones nowadays, if you have a piece of code compiled for ARM and you want to run it on an x86 processor because Intel wants to implement Android or something like that, then now we have a way to describe situations like that as well. So I'll talk about that briefly at the end. Okay, so I want to start by talking about why we need memory consistency models in the first place, just to make sure everybody's caught up. And then from there, I'll move on to my focus on hardware and then into the microarchitecture space. So first of all, why consistency models at all? Why do we even need to worry about this? And so I tend to think of it as being along a spectrum, something like this, where on one side you have this notion that things tend to be strongly ordered and everything is more intuitive that way. If I'm a programmer and I say that I have a store to X followed by a store to Y, it makes sense to me that everything would stay in that order all the way through. It starts to get very hard to reason about things, especially in your head, if things are getting reordered compared to the order that you write them down in originally. On the other hand, if I'm an architect, which I am, and I look at what I can do to improve things like performance, what I would say is I would be a good architect, I would do my profiling, I would see that most accesses tend to be private to a thread, they might be accesses to a stack or to private variables, things like that. And if that is the common case, meaning that that we don't need to worry about strict ordering for private accesses, then I can say I might as well reorder them and let them not worry so much about whether they appear in different orders to different threads, things like that. And in particular, from a microarchitectural point of view, that allows me to add things like store buffers and write coalescing buffers and things like that. So if I have a cache miss on the store to X, I don't have to have the store to Y and the load to Z and everything else waiting in line behind it. They can actually go around it. They don't have to wait in line. So on one hand, I get more intuition. On the other hand, I get better performance. And at least from a hardware point of view, as you can see in the middle on the spectrum here, there's really no single answer to this question of where exactly do we fall in line between these two extremes. There's been some strong memory models in practice. There have been weak memory models in practice. And it's really, so like I said, there's no single answer, and it's even a challenge to define where exactly these things are. It's not necessarily even a simple spectrum like I've drawn it here, but really it's a challenge to even figure out how to write down some of these models in the first place. From a software point of view, what it looks like is this, where we would say that because we want to write portable software and we don't know how any particular piece of hardware is going to behave in terms of memory reordering, what we would say is that certain things we have to write our software in a portable way that doesn't rely on any particular ordering constraints. So a situation like this, where we have a typical memory consistency model Litmus test, or a test written to test a particular feature of a consistency model. This one is called message passing, and what's going on here is that we have the producer wants to send a message X from the producer to the consumer, and the way we do it is to say we have a store to X followed by a store to a flag Y that says the message is ready, and then on the consumer side we do it in the other order. We read the flag first, and then we read the message to see if it's the value that we know we should be expecting in this particular case. And so if we go back to the hardware picture where we don't know what reorderings are possible, it's possible that either the compiler or the hardware might take these two stores to X and to Y on the producer and reorder them, and then we get behavior that doesn't make sense. So from a software point of view, this is considered to be a data race, which is ruled out as illegal because we don't know what's going to happen in the situation of a data race. So what the software people have said over the years is that rather than having undefined behavior like this become possible, we just rule this out and say the only way we can have communication between threads is to say we have to have explicit synchronization between them of some form. So maybe it looks like this. Here's an example using C11 atomics, although the same might be true whether it's mutex unlock and mutex lock, or maybe it's even GPU kernel, end of the kernel, and then wait for the end of the kernel on the other side. Whatever the case might be, sometimes these things are wrapped up in higher level constructs. But the idea is the same, that we need to have some kind of explicit synchronization between the two different threads to make things happen correctly. And then so what it looks like is we have, in this particular case, we have the C11 notions of sequenced before and synchronizes with and so on. But really what we want to do at some higher level is to say we have this happens before relationship between the write of X and the read of X to say that the write had to happen before the read, and therefore the read is going to return the correct value. And then, so the question is, so that's from a software point of view. The hardware point of view is to say we actually do want to specify what reorderings are happening, because at some level, these synchronization constructs shown here are going to have to turn into whatever synchronization is necessary at a hardware level, whether that's preserved program order, meaning things just naturally stay in order, or sometimes you have to insert fences to restore the orderings, things like that. The first question is, how do you even specify what needs to happen in the first place? And then the second question, like I hinted at in the beginning, is to say, even once you specified it, that's great, but then you have to still make sure that what you've specified is what's actually happening on a particular microarchitecture. And the additional challenge there is that there can be lots of different microarchitectures for any one given architecture, right? If I have, say, an x86 specification, I can implement that as a processor with a store buffer and see total store ordering, TSO, as required. I can implement that as a sequentially consistent core, and that's strictly stronger. It allows fewer reorderings than TSO would, but it's still a correct processor. And even within TSO, I might have the small core Atoms that's maybe an in-order core. I might have a big out-of-order processor, superscaler, all kinds of things that might happen. Whatever happens at the microarchitecture still has to be implemented correctly according to what the architecture says. So that's what my talk is going to be, or my PipeCheck talk is going to be about. And so the first thing you might do to specify what a hardware memory model looks like would be something like this. This is the kind of detail that you tend to see in architecture level specifications, where on one side I have x86 total store ordering, on the other side I have some approximation of what the power memory model is. And so the general idea at a high level is to say that if I have a pair of accesses in program order from the same thread, maybe a store followed by a load or a store followed by a store, if that's the case, then I need to know whether that pair of accesses is reorderable or not. So on x86, the only pair of accesses that are reorderable are a store followed by a load, whereas on power, it's pretty flexible. Almost anything can be reordered. So it looks like it's simple enough to write down what's going on, but unfortunately, it's actually more complicated. So if I ask Jod what the memory model for a power would be, it's not going to be that. It's going to be something much, much more complicated, where it has dynamic behaviors being added in. It has you have to find the fixed point of some recursive definitions of instructions in the chain, in the pipeline here. It's much, much more complicated than just saying that it's this nice little table here. So
I've got a much more basic question than fixed points. So if I say store 3 into X and then store 4 into X, surely even on the power, I'm not going to end up with 3.
Yes, exactly. So even for x86, which looks much simpler in comparison, even this is not sufficient enough to describe all of the behaviors of the memory model for the reasons you just described, that there's more to it. There's
If you store it at the same address, you can't reorder, presumably.
Exactly. There's things like that. There's things like multiple copy atomicity. There's things like dependencies, all kinds of stuff that has to get added into the model to really get a fully complete description of what's going on. So even this piece that I'm showing here at the bottom is just the preserved program order part of the power memory model. It's not even talking about all the address and data dependencies and the behavior of different fences and things like that. It's really, it's much more complicated than just saying it's this little table here. And that's exactly the point, is that it's a challenge to write these things down and to know that it really captures all the corner cases of the model. You can write down tests that are 6 or 7 instructions in size and still not know nowadays, even still, how those particular tests behave. So it's really challenging. But yeah, that's a good point. Okay. So anyway, once we have a model, assuming we do have some model, and we've made good progress as a community in figuring out how to write these down and improve them to make sure we have complete coverage, what we then do is we take this particular litmus test, and here's a more abstract representation of the same software example I showed earlier, the message passing test. And what we do is we write it down in such a way that we can draw something like a happens before graph, or at least this is one approach, the axiomatic approach, to draw a happens before graph based on what we see either in terms of static properties such as preserved program order, which I just showed, or based on dynamic properties such as one instruction reading from the value written by another instruction. So here's an example showing, like I said, MP, message passing. And in this case, what we have is a preserved program order relationship because a store has to be ordered with a store. We have a reads from relationship based on the fact that if we say register R1 is returning the value 1 based on our hypothesis, and the only place it could have gotten that value is from instruction I2, the only thing that's storing a value of y of 1 to y. And then we have another preserved program order relationship on the right side, and then we have what's known as reads from earlier or from reads, in which case I4 executes and returns its value before I1 in this case writes 1 to x. And so what we have here is a cycle in the graph, and what that would mean intuitively is to say that an instruction happens before itself somehow, which is, it doesn't make sense for that to happen. And so what we say is that a cycle in this graph means that an execution is forbidden.
So that, quick question.
Sure.
This read from arrow relied on something you said, the only place you could have gotten that 1 from would have been this store. That sounds like a sort of fuzzy concept.
So
right?
it's a good question.
The only place it could have got this value from.
So we do two things along those lines. First of all, we generally assume that everything is zeroed out at the beginning of time just to make it easier to think about. But then in general, and more importantly, I think that if you have an execution that might have lots of different stores of a particular value, then what you would do is you would check all the different possibilities. So if I had lots of different stores to 1, I would first check the scenario where this load reads from the first store, and then I would check a different scenario where the load reads from the second store, and so on. I would have to check all the different possibilities. And so for a small litmus test like this, where we're writing it for a particular purpose, it's generally written with the intention of having to force it to read from a single location by design. But in general, from a broader program, it could be much more complicated. There'd be lots more dynamic scenarios. OK, so this would be the... Oh, go ahead.
So in this example, how did you know to have a different relation for reads from and reads from earlier? I mean, is it clear from the code on the left that you need to use these two different relations, or could they both be reads from?
So in this case, it's because it depends on the value that gets returned by each load. So if we say that R1 has the value 1 at the end of time, that means that I3 must have read the value from I2, because that's the place that it got 1 from. On the other hand, if I4 returns the value 0, then it couldn't have happened after I1, at least from the point of view of I4, because it returns that value. Otherwise, it would have returned the value 1. OK, so that would be the nice case, is if we could just say cycle equals forbidden, no cycle equals permitted. But unfortunately, because of all the more permissive consistency model behaviors, what turns out to happen is more something like this, where we have a slightly different litmus test, again small, but what's going on here is we have a store to x followed by a load of x, and then on the other side we have a store to y followed by a load of y right away. And what happens here is we can do the same kind of analysis. We can say that there's reads from edges, there's preserved program order edges, there's from reads edges, and again it looks like we have a cycle. But what happens in this case is because this reads from edge, these two reads from edges actually represent potentially at least forwarding from a processor's local store buffer, it turns out that this particular case, a cycle, this outcome is observable in practice, and hence a cycle is not enough to say that this outcome is actually forbidden. And so what we need to do to actually capture all the details of consistency models is to say that we either need more complexity in the way we describe our edges, which is one approach that works, and you can say that maybe reads from internally, reading from the same thread is not something that participates in your cycle finding process, or it doesn't compose transitively with other edges the same way that PPO or from reads or different edges might, depending on your consistency model. A different approach would be to say that rather than adding complexity to the edges, you add complexity to the nodes. And so in this case, what you would say is take a particular node that was there before as one single thing and split it up into different pieces, maybe performing once with respect to yourself, and performing at a second step with respect to all the other processors and all the other cores in the system. Or in general, there might be multiple nodes that a particular single node splits into as you go. And so in this case, if I draw the separate nodes, you can see that, again, there's no cycle in the graph. And so what you want to do is either you add the complexity to the edges and figure out which cycles actually do mean something, or you split up the nodes, and then you can get back to the point where a cycle does correspond one-to-one, hopefully with a forbidden execution. And so for PipeCheck, what I'm going to do is I'm going to take this approach to say split up the nodes and really map that deeply into what the microarchitecture is doing. I think this is a more intuitive notion for what happens at the microarchitecture. So what that looks like here is if I go back to the message passing example for just a second, if I use this analysis where I split up the nodes into different pieces, and then I want to figure out how this litmus test gets mapped onto this particular store buffer, or this particular 5-stage pipeline with a store buffer. And so, like I said, what I'm going to do is I'm going to split up these I1 and I2 stores into different nodes. And it's going to look like this. And I'm going to make a correlation between these different nodes and different pieces of the microarchitecture. So I have these two nodes in the expanded graph represent accesses entering the store buffer, and these two other nodes in purple represent accesses reaching main memory.
So the fact that you split the nodes into just two nodes is pretty arbitrary, because, for example, basically the way I view it is there exist multiple internal states that are somehow observable to others, let's say. So it could be the case that you don't have to split like the node into just one node, but multiple ones in the middle, and then have different guys being able to observe different intermediate things, right?
Absolutely. So that completely depends on what the architecture says. So for something like x86 TSO, then maybe 2 nodes is sufficient. For something like Power, ARM, things like that, then you might have to expand it in a lot more nodes. So I completely agree with that. There's also the distinction I want to make, especially from a PipeCheck point of view, that there's a difference between what the set of things that might be permitted on any given architecture by spec and what any particular single implementation allows by spec, and even those two might be different. And so that's exactly the comparison that I'm going to draw here.
But then intuitively, you're splitting up the nodes is sort of a way to capture the different visibilities of stores, basically. Is that sort of the starting point of how you split the nodes, or is that a wrong assumption?
No, that's exactly correct. That the store might become first visible to the issuing processor because it's in the store buffer, and then so any subsequent load would come along and be able to read it. But while it's sitting in the store buffer, the other threads may not be able to read it yet. Exactly.
One other question. When you separate these events out, you come up with some microarchitectural picture like the one on the left. How do you know that it corresponds to the actual microarchitecture of the processor?
So that's the rest of exactly the upcoming slides. So actually, if I click next, if I go back to this picture, and then what I'm going to do is translate this picture on the left into a much more expanded graph. So it's not just about the points where it reaches memory, but where it actually reaches each individual stage in the pipeline, stage by stage. And I'm going to create what I call a microarchitectural happens before graph, rather than just the architecture level happens before graph. So if I work it out, I still have this same correspondence between nodes in the previous graph that I showed in orange and purple and microarchitectural locations, but now it's not just those two. It's actually, those are just two among the many possible stages in any particular microarchitecture. And again, like I said, this may be different in some implementations. Maybe there is no separate orange and purple here. Maybe it is joined together, and that's legal. It might be a legal implementation, but it's really what we want to do is compare what the spec said on the previous couple of slides to what a particular microarchitecture is doing on here. Okay, so let me zoom in on different pieces of this graph to show you how it's created step by step. So I'll start in the corner here. So the first thing we do is to say that program order is something that happens at the fetch stage. That's our starting point. But what we don't do is we no longer assume anything about preserved program order. It's not something that we say that we're going to assume somehow that accesses remain ordered when they get to the point of view of the cache or the memory hierarchy, for example. Instead, what we're going to do is only assume program order at the very beginning of the pipeline, and then for everything else working down the pipeline, we have different arrows representing just behaviors at a stage-by-stage level. So, for example, what I'm showing here is an in-order pipeline, and so I can say that maybe the decode stage has 2 instructions that come in order, and I know something about the decode stage itself as a self-contained unit. That is also an in-order stage, so if things come in a certain order, they also go out in a certain order. And so that translates in the graph to say that if I have this blue edge on top, or any edge on top, coming into the decode stage, then I also have the corresponding edge going out of the decode stage. And in this case, that can propagate all the way down. I also have the path of each instruction as it executes, going from fetch to decode to execute and so on down the pipeline. And again, this is another example where we might have multiple different scenarios depending on the fact that there might be different paths that an instruction can take. If there's maybe different parallel pipelines that a single pipeline might split into different paths somewhere, or loads and stores might take different paths through the pipeline. If there's multiple possibilities, like I said before, we enumerate all the different possibilities and create a graph like this for each of the possibilities.
So which stage would be missing if the execute stage was not in order in this particular example, for instance?
So in this case, it would be in order all the way down until at some point, if I have, say, an out-of-order issue stage, which I'll have in a couple of slides, then I would be missing one of these arrows going across.
These are cross arrows.
Exactly. And then also not just that one arrow, but then everything else that would depend on that arrow would also be missing in that case. So as I work my way down, I also have the reads from and from reads edges that I had in the architecture level descriptions. But then what happens as I zoom in is I actually have a particular point in the pipeline where these microarchitecture or these reads from and from reads edges are also taking place. So for example, if I translate a reads from edge that we saw in like we saw in the message passing litmus test before, one possibility would be to say that a load, when it reaches the memory stage, it's reading from a particular instruction that must have passed through the main memory hierarchy. And so we have a reads from edge from this, what I call a performing location in the pipeline. So from this performing location for the store to this performing location for the load up in the corner. But that's not the only possibility, and this is one of the reasons why I like that more complex nodes instead of the more complex edges scenario, is that maybe this is one possibility, but if I draw it a little bit differently, if I want to reflect the fact that accesses might enter the store buffer a little bit early before they reach main memory, then I can have different possible outcomes as well, where reads from edge goes from a different performing location to the load's performing location. So I have two different possibilities that I can check, and they could potentially lead to different outcomes in the end. And in other words, maybe one could produce a cycle and the other may not produce a cycle. And so not only does this tell us why the multiple node graph is maybe more intuitive from a microarchitectural point of view, but it also gives us some idea of why exactly different scenarios give us different executions. So it might point out explicitly that it's something about store buffering and it's something about an access not having reached main memory yet, or something like that. So if I go back to that 6 instruction litmus test that I showed a little bit earlier, there was the one that motivated us to have to add this added complexity to the graphs. This is a great example of why having the microarchitecture level detail helps in that case. So if I treat this, first of all, as a scenario where every instruction has to access main memory and all memory accesses are performed through main memory only, then I do get a cycle in the graph, and there's no way that that can happen, that forbidden outcome can happen. But on the other hand, if I add the store buffering behavior in and I have the reads from edges performing at different locations within the pipeline, then I have a different graph that looks like this, in which case there's no cycle in the graph. And so not only is the outcome allowed, but like I said before, we actually have some more intuitive notion of why that outcome would be observable on this particular microarchitecture. And then following that, like I mentioned for preserved program order, what we would want to say, if we want to go back to those tables or the more complicated form of those preserved program order tables that say maybe a store to store in this case has to be ordered with each other. And so what we would want to do is to check that the first store reaches the main memory or the memory hierarchy before the second store reaches the memory hierarchy. That would be our condition for a preserved program order. And so what we do from a microarchitecture happens before graph point of view is to say that we have a graph that looks something like this. Maybe we have some extra edges in there to reflect some special behavior of the store buffer. So in this case, we would say that maybe the store buffer only allows one outstanding access at a time, and so we get this diagonal green edge. And if we put all these edges back together, whatever they may be, and we can say that that arrow that we were looking for preserved program order is actually a consequence of some sequence of microarchitectural edges. It's not just something that we have to assume anymore. It's something we can actually check for directly. So that's also great. We now have a way to check this kind of thing directly, and it's it's a great way to verify that whatever we expect to happen from an architecture point of view actually is happening in all the different scenarios of a microarchitecture point of view. One of the other nice benefits of having a level of microarchitectural detail is that it also allows us to model things at a microarchitectural optimizations that simply can't be addressed at all by architecture models because by definition they're meant to be independent of any particular microarchitecture. But then what that means is you have all kinds of crazy things like speculative load reordering and out-of-order processors and fence speculation, all kinds of stuff that's happening at a microarchitecture level that just can't be described in those models, and now we can have a way to describe them at a microarchitecture point of view and still verify that what they're doing is legal according to the spec. So in this example, I have a case of speculative load reordering where what would happen is to say that if I have two loads that are supposed to be in program order and in preserved program order with each other, but suppose the first load has a cache miss, well, the second one has a cache hit. From a microarchitecture point of view, what tends to happen in some processors is that the second load will execute speculatively. It'll say, just read the value that you have for now and move along, assuming that it's correct. And when the first load comes along and actually does get a chance to execute, that first load executes, then the second load can now safely check whether the speculation it made earlier was correct. If it was correct, then you just keep going and you've gotten your performance benefit from speculation. If it wasn't correct, then you go back and flush that second instruction and everything that came after it and retry it with the correct value. And so from a consistency point of view, what that means is that strictly from comparing when the two loads reach the execute stage, they might not actually execute in order. They might actually execute out of order and still have it somehow be correct. And so from a microarchitecture happens before point of view, what we do is add features like saying this particular edge, again, this is a message passing litmus test, where we have the two loads that are supposed to be in order. If they are not actually executing in order, what we say instead is that we can model some features of the microarchitecture, in this case, checking for cache line invalidation, if that's the way that the speculation is implemented. We can say that preserved program order actually is implemented this way. We're tying into the fact that speculation is actually part of the pipeline. And so we still have the cycle assuming that our speculation is correct, and we have a way, more importantly, we have a way to model this speculation without just saying that it somehow magically still meets the specification without knowing exactly how it does it. This PipeCheck approach tells us a more fine-grained way to analyze exactly why speculation is correct in what it's doing. And the other nice thing is that this PipeCheck approach it's not limited to homogeneous pipelines. So if you think back to the motivation that everything is becoming more and more heterogeneous, PipeCheck itself can easily extend to heterogeneous pipelines as well. There's nothing fundamentally different about it. We just have different sets of stages on one side than we do on the other side. The same holds true, the same analysis still works even if the pipelines are heterogeneous. So what we did to test PipeCheck is we actually implemented it as a tool that does all of the enumeration of different graphs and all of the checking for cycles and things like that automatically. All you do is you specify the behavior of a particular pipeline, again, at a stage-by-stage granularity to say that maybe the decode stage is in order, the issue stage is out of order, whatever the case might be, all the way down stage by stage. The definitions of the microarchitectures themselves are not all that big. You can see they're just maybe up to 100 lines or so of code, even in the most complicated case. And we have anything from the very simple pipeline that I showed earlier, the 5-stage pipeline, to the Gem 5 simulator pipeline, the most detailed model, to the OpenSPARC pipeline to get more of an industry strength pipeline also modeled in there. And so we write down the set of stages in the pipeline, the set of performing stages, as I talked about earlier, and so on, some of the other little details that we need to add into the model. And we take that, and PipeCheck then performs all the analysis to say that what I want to do is I know from an architecture point of view, from some of the other work and the other tools that are out there, I can say that I know whether a particular litmus test is forbidden or permitted by the architecture specification. And then I can also take the PipeCheck model to see whether it's observable or not observable on a particular pipeline, a specific instance of that architecture, and then I can compare the two to each other. So sometimes there might be a match between them if it's permitted and it's observable, or if it's forbidden and not observable, then that's great. I might have a scenario where an outcome is permitted but not observable on a particular pipeline, which is also correct. There's nothing wrong with that. It is a quantitative way to say that a particular pipeline is stronger than it needs to be in terms of memory consistency. On the other hand, if I have a scenario where an outcome is forbidden, but it turns out to be observable on a particular pipeline, then that's actually a bug in the pipeline. And not only have we found it then, but PipeCheck gives us a way to actually zoom into the microarchitecture and figure out exactly where that missing arrow is and what we think we might need to do to fix it, what might be the missing edge in there.
If you say that you enumerate all possibilities, it makes me shiver a little because I think it's quite a large number. Is that intuition wrong, or are you clever about pruning the whole search space?
So that's a great question. So fortunately, we don't need to be particularly clever in this case because it turns out that most of the litmus tests tend to be very small. They're no more than 4 to 8 instructions in size usually. And so what that means is you have a graph that's maybe a dozen or so pipeline stages in length and maybe 8 instructions across, and it's on the order of 100 nodes in a graph. That's very quick. So if we were to extend this naive approach to testing broader programs as a whole, it would run into the state space explosion quickly. But for litmus tests, that's not the case. It tends to be very scalable, and I'll show some results in a second.
There must also be some kind of small model thing where it doesn't if you can just test all kind of small programs, then just be completely sure that you've done everything right. Just test small examples.
Sorry, I missed the.
So you can test small examples, and that would give you some kind of completeness for kind of all possible examples or something like that.
So that is a great question, and I think if I understood the question correctly, that you can test some set of test cases, but you don't know if that's complete.
All I'm saying is it's probably doable to find a set of small test cases that is complete. That's my conjecture.
So what we do have, I don't have any particular proof that anything is complete. What we do is check directly for preserved program order, first of all. And then we have the fact that researchers in the past, some people in the room even, have come up with large suites of litmus tests over the years to test all different cases that they can think of, and even use computers to generate lots of different cases and really try and make it as exhaustive as possible. So I think that's really what we're going for, is as much coverage as we can get from litmus tests, and hopefully that tends to be 99-point-something%, and whatever that means. I mean, there's no way to, or at least at this point, what we've done so far, we don't have any formal proof of completeness given a set of litmus tests, but we just try to be as exhaustive as possible and pull from others who have done similar approaches.
I think my concern would be that, yes, if you find a bug, you'll know that your abstract view of the pipeline has a bug, right? That's the good thing. But the lack of such evidence, in particular if you only can test the small litmus tests, is not a very strong indication that your pipeline is actually bug-free, right? Because you might be missing a lot of practical corner cases that are not part of the litmus testing framework, right? Intentionally so, because it only looks at the memory instructions. So you might be missing the ugly cases where you have many branches, for example, or other instructions that are not usually part of litmus tests. So I'd be curious to see what future work, I'm sure, is you might be looking into to kind of tackle that point actually.
That's a great question. I think even another concern that tends to come up, especially when I talk to companies about this kind of thing, is that maybe a particular load, or it looks like a load from an architectural point of view, gets maybe split into multiple loads in the microarchitecture because it's an unaligned access or something like that. Yeah. There's all kinds of stuff, and branches. So we don't have any 100% guarantee that if this works, that everything about your pipeline is correct. We're just trying to get closer and closer to it and provide a general approach that says if you need to split up a particular, I don't have a picture anymore, but if you have a particular load that you want to split into different loads, then that works. The same approach still holds true, and you just check whatever you might have. And then ideally we would be able to say something like, it's not just preserved program order, but we would check that any fence constraints are guaranteed directly, not just through a litmus test, but through that replacing an architectural edge with a sequence of microarchitectural edges, that kind of approach. That would be the more general case that would make me at least more comfortable that everything is complete. But litmus tests are a great sanity check, if nothing else, and they tend to have pretty good coverage.
So your examples are abstractions of existing microarchitectures, right?
Yes.
Are they tight, the descriptions? Did you try weakening them and see whether they are still in the memory consistency model?
So in some ways, actually, we may not have intended to do that, but sometimes that is just part of the natural process of coming up with the model, that we would, so for example, the first time we would come up with a model for a microarchitecture, it might come back as having failed a few tests. And what that might mean is not that the microarchitecture is broken right away. It might just mean that we missed something about the model that we need to go in and say, oh, this little piece is actually stronger than we need to. It's stronger than we thought it was in the first place, and we have to go figure out why that's stronger and then check the updated model again, things like that. We didn't necessarily go back and check whether things are minimal because, in general, they may not be minimal. The pipeline might be over-constrained, and that's still a legal way to build a pipeline. So the goal of the approach anyway is to say that, first of all, we would want to be true to what the microarchitecture is doing, but then beyond that, what we are hoping to do is to say that we're reducing the burden from having to check something about the chip as a whole with billions of transistors on it, and instead just zoom into particular stages and say that maybe I have the RTL for a decode stage, and it's much easier to say something about the decode stage being in order as a self-contained unit rather than having to verify the whole chip all at once. And so we're really just trying to zoom into individual stages and make the burden for the verification of RTL to say that you're verifying local properties rather than any big global properties all at once.
Did you try finding the minimal such descriptions, say for 5-stage, 6-stage, etc.? Then you can just make a graph inclusion problem, the whole verification.
Yeah, so maybe a different approach or a different interpretation of that question would be to say that if I'm ARM and Power or people like that, I want to have the weakest possible implementation of my already weak spec, and I want to squeeze as most performance as I can possibly get out of it, then I could do exactly what you said, try and take the minimal graph that is correct and use that as my microarchitectural goal. And so we haven't tried that yet, but it's an interesting idea that, yeah, we could try in the future. Okay, so we have this tool. It does all the enumeration for you. And just to quickly reassure people that were asking about the performance and the state space explosion, this is just a numerical proof that it doesn't blow up in practice. So this is testing I don't know if I mentioned this before, this is testing all x86 pipelines. At least at this point, we were focused on preserved program order as our primary verification step, and we're hoping to extend that to other features in the future. But we were testing preserved program order, and we were testing the Litmus tests for x86. So those are shown as the different cases along the x-axis. Along the y-axis, we have the runtime, and along the different bars in different colors, we have the 4 different pipelines that I showed. And as you can see, even in the worst case, it's no more than a few minutes to run all different cases of the Litmus test, check all the graphs, and make sure that everything is correct. And this is even true, actually, even though we actually implemented this tool in Coq, it's a theorem prover, which is we're trying to start from a more formal basis to begin with, so we can also connect to other more formal verification tools at some point in the future. Ultimately, we want to have this be part of a rigorous stack, maybe all the way from software down to hardware, down to microarchitecture, or from software to architecture to microarchitecture. And so our goal was more on correctness. Our focus was on correctness rather than performance. And so this is all the performance numbers of a tool that's auto-extracted from Coq to OCaml and then executed in that case. If we were really optimizing performance, we could have really squeezed this even further. This isn't really an upper limit of performance. This is just doing the most naive thing, and we still get really satisfactory performance even in that case. So that's one of the great takeaways of this is it's a smarter way to verify things at a microarchitecture level without even having to worry about state space explosions or unscalable verification or anything like that. And the other thing we can do is look at particular Litmus tests that come up and say, if I want to know exactly what worked or what didn't work on a particular pipeline, that gives us a lot of information as well. I can say that across the 4 pipelines, 2 of them matched everything exactly what the architecture said. In one case, in the simplest pipeline, which didn't even have a store buffer, that was just the 5-stage pipeline, then there are some cases where an outcome is allowed by the architecture but not observable on that particular pipeline because it doesn't have a store buffer intuitively. And so PipeCheck finds that for you and points it out to you. And again, like I've mentioned, it's not a bug. It's just interesting to know that you have some quantitative way to say such a thing. On the other hand, in the Gem 5 pipeline, and as others also observed in parallel to us, there used to actually be a bug in the way that it implemented load-to-load reordering. It implemented it correctly for accesses to the same address, but not for accesses to different addresses. And so there was a case where the illegal outcomes, according to the architecture, actually became observable on that particular pipeline. And so PipeCheck highlighted those as well. And then that lets us zoom in on exactly what went wrong and figure out where in the graph to draw that missing edge that we think needs to be there to forbid these outcomes again.
Is the root cause of all of these observed that reason?
Yes. In these cases, that was the bug. If you fix that one bug, then all of these go away. Yes. Okay, so that is the conclusion for a PipeCheck, that we have this nice quantitative and more rigorous way to compare what a microarchitecture does against what the architecture says should or shouldn't happen. And it lets us do all this verification in a much more rigorous way. It lets us do it in a scalable way. And we have this tool that you just give it the model, and you tell it local properties that are much easier to check individually, and it puts them all back together and does all of the analysis for you to verify that the microarchitecture behaves as it should. Any questions?
I'm curious, what's the advantage of using this tool over running the actual litmus tests on the actual implementation directly? What is the difference that you learn? I mean, I think you have that extra indirection of someone having manually to carve out that abstract pipe description from at least Gem 5 is really messy code, and I've been in there. So what do you learn about understanding, well, your abstract pipeline has a bug? How hard is it to translate that back to, well, actually the real thing had a bug? And what's the comparison to running the actual litmus test on the thing?
So I would say that this isn't necessarily meant to replace running it actually on the processor, because that's really the greatest way to check whether it's observable or not observable in practice. What I would say is that in the past, there have been papers that have done, there have been plenty of papers and research about how to just run the test, and then if you see a failed test, you have to do some detective work to say, where exactly did this go wrong? Is it somewhere early in the pipeline that it went wrong? Is it somewhere maybe just the store buffer was only supposed to let out one thing at a time, and it actually let out lots of things at a time, or things like that? Without having some more zoomed in view of what's happening, you don't necessarily know where to look, and you have to just look all over the place. Whereas if you have the microarchitecture graph, you can say that I'm looking for an edge between these two nodes, and so I know that there must be some edge somewhere in this vicinity. Maybe it's because of the store buffer diagonal edge that I showed earlier. Maybe it's something else nearby, but it's probably somewhere here because I know that maybe everything else is in order already, and so it probably isn't in that domain. So you do have a little bit more, knowledge to work with in doing that detective work. And then the other nice thing is that we do have, it does lower that RTL verification burden, assuming you get your microarchitecture description correct, to only having to verify things at a stage-by-stage granularity.
Right. Yes, yeah. But I think that last point is the critical one, where you have to be lucky enough in a way to replicate the bug in the microarchitecture in your abstract description, and I'm wondering how likely that is. So how did you replicate the bug from the Gem 5 pipeline in your description? How did that sort of happen? Is it easy to reconstruct that sort of process?
So at this point, it was pretty much a manual process. We did have to go into that messy code and try and come up with that model ourselves, and that was a little bit of an iterative process.
And you were sort of basically, you captured the buggy interleaving as well in your model as well. Because I think these things are not really obvious, right? They kind of are lurking corner cases, I presume.
Yeah, so actually, in this case, for the Gem 5 example, it wasn't actually our intention to create the microarchitecture to find the bug per se. We were going in assuming that it was correct. Right. And we came up with the model, it showed a bug, and then we kept pushing on it. And eventually we said, we can't figure out anything else in this code, or you could say the same thing about RTL. We can't figure out anything else to say about the RTL. Maybe it actually is a bug. Right. And then once we did that, we actually did go back and run the litmus test on the simulated hardware. And then we said it is actually observable, and here's the proof.
Yeah. Thanks.
Is there any hope that this would be compositional on the level of instructions? Say if I want to run your tool on something that has more than 3 or 4 instructions, is it going to have to build a gigantic graph and run through the whole thing, or can you somehow split it up into smaller graphs?
So that is the goal, to make it compositional, and that's, I think, one of the benefits of the more complex nodes case as opposed to the more complex edges case, is that if you expand the nodes, then you don't have to worry so much about edges not being transitive with each other. If we just have, in this case, we have a microarchitecture happens before edge, a microarchitecture happens before edge, and they're all transitive with each other. And so you could compose them with each other. You could compose either different stages with each other, or you can compose different instructions side to side with each other, and it should all work correctly. So we haven't pushed as hard on this for things like the power memory model yet, but that's still the goal, is to make everything be composable in exactly that way, because we think that really helps it be scalable for exactly those reasons.
It seems to be set up to get some sort of abstraction layer just above, because you could express this in COC and actually get the proof from the underneath layer.
Yeah, exactly. We started in Coke, like I mentioned, as a way to ultimately make it formal. We haven't gotten to that point yet, but that would be something we could definitely try and push on. Yeah.
You might have missed this, but how do you relate your pipeline models to the models of the actual microarchitectures you're studying, especially if they're proprietary ones?
So that was actually the challenge. I mean, so this was a collaboration with Intel, and even so, they weren't willing to release any Intel microarchitectures to us and have it be publicly published. And so that is part of the challenge, that we're just trying to get our hands on as many pipelines as we can and just keep implementing them and see what comes out of it. And so we did manage to get the OpenSPARC, which we were happy about, because that is a commercial strength processor that we were still able to model. But it is a in-order processor. It's very parallel, but it is still in order. And so if we can get more microarchitectures that are available, then we would love to keep adding them. We're just working with what we can get as academics instead of industry researchers.
I haven't really understood just how microarchitectural your microarchitectural models are here. So the diagrams that you show look as if you're more or less just splitting events, splitting write events and read events. Is that actually all that you're doing?
So
a bit more context. So you could imagine a more concrete operational model, let's say, in which you have all the details of how instructions access registers and how that gives rise to dependencies and all of that kind of thing. Is that part of the modeling here?
So that particular piece of it, the registers and non-memory accesses, at this point are not part of the model, although we could potentially add them in and they would flow through, and theoretically they would flow through the pipeline in the same way and just not flow through the store buffers or things like that. So in order to model dependencies, register dependencies and things like that properly, that would be probably one thing that we would need to add, at least in some way, to capture all the details of that. But from a higher level point of view, although I did describe things as being a stage-by-stage level and instruction-by-instruction level, even that does have some flexibility in exactly how detailed you make stages. So if you think of execute stage might actually, if you get deep enough into the microarchitecture, it might actually look like 3 or 4 different stages. And so you could expand that just as easily. Or at the same time, if you were worried about verification time or things like that, you could even compress, fetch, decode, rename, and so on into some single stage and say this whole thing is in order. I don't need to worry about the fact that it's 3 different stages because they're simple enough that I don't need to draw separate edges in the graph for them. So you do have some flexibility to figure out exactly what level of detail you want to zoom into and then make your graph accordingly.
I would imagine that most of those extra nodes are irrelevant. Right? The only ones that matter are the ones that you can read from or that create a dependency.
Yeah, so in that case, it becomes a balance of, do you want to have more nodes in the graph and therefore have a little bit longer verification time potentially for PipeCheck itself, but then the trade-off is that the microarchitecture level specifications you have are much more fine-grained and then presumably much easier to verify as local properties, whereas if you go the other extreme and compress everything together, maybe you save PipeCheck some time, but then you have more of an individual verification burden to say that the whole front end of my pipeline is all in order as a single unit. So we picked one spot in here that we thought was a good way to correspond things to the way architectures might be described, but then you do have some flexibility to tweak it one way or the other.
Are your models finite state? In particular for the TSO description, do you bound the size of the store buffer?
We do not bound the size of the store buffer in this case. So from an architecture point of view, they generally tend not to either. If it were something that was fixed in the architecture, then it could be that way. But usually it tends to be just something, this is a particular microarchitecture has 8 or 16 or something entries, but that's not something that they want to guarantee for the rest of the life of the TSO consistency model or something, and so they don't generally put it in.
Have you developed any kind of notion of refinement on these graphs that could be useful for, like, so what Peter was saying about the optimization, you could actually prove that the compression of some events into one was not observably or didn't introduce any new behaviors? Or
so we've thought about it conceptually in that way, but we haven't actually gone in and proven things per se, although the idea would look exactly like it does for preserved program order, the way we verified that what we expect to have, or on PPO we have some edge that we're expecting to replace from some sequence of microarchitecture edges. In this case, it might be the other way around, that we have some sequence of microarchitecture edges that if you squeeze them together, they result in just this coarser grained edge. But the similar idea would be there because of this transitivity property that we're going for. Yes?
At the start of your talk, you mentioned a couple of actual bugs that have been found on real-world processes. Does this approach, do you think, could be extended to find those particular bugs? And if so, how far away do you think you are from being able to do that?
So yeah, the bugs we did find in practice were just in that simulator Gem 5. We didn't find any bugs in OpenSPARC, for example. So that is reassuring, but in the future, it would be nice if we could get to the point where if Intel is trying to model this transactional memory implementation that they just came up with, then they could use PipeCheck to say that this is working correctly according to the microarchitecture model that we have, and therefore have some more reassurance that it's correct before releasing it out into the wild and only then realizing that something went wrong with it. And so, yeah, we haven't gotten it to the point of being used within industry in that kind of scenario yet, but we're hoping that by spreading the word, we can convince people to start thinking along those lines.
Some interesting, sort of not real evidence, but I happened to work for the company at the time that had the first bug, so for AMD. And without disclosing any of the details, but the specifics of that bug were sufficiently obscure that I don't think a manual translation of the pipeline into that would have found it. That's why I was kind of pondering the question earlier, that you really have to be lucky for some of these guys to really find this. So, yeah. Which is a bit of a downside, really. But
yeah, so I think what would be more ideal maybe is if we had some more automatic or semi-automated way to get from RTL up to specifications like this. And that's, yeah, it's a little bit farther out at this point. We're hoping that we're at least narrowing the gap somewhat, and then that can be a starting point for future research to say this is what we need to target rather than just targeting the specification as a whole. But yeah, it's not there yet. That would be a little bit farther down the line.
I think there's just the one half of the coin that you need, and the other one is that, well, there's a question from the back there. The problem is not just the litmus tests themselves in their pure form, right? You oftentimes have to have these other instructions, and when you run the actual litmus tests, Judd and Luke make sure that there is a lot of irritation around the actual pristine litmus test, right? And then you, in many cases, actually need that extra irritation around the core of the test to bring the microarchitecture in that state. For example, if the store buffer has only a specific size, just need to have a single entry more that rolls off, and you find the corner case to hit this. So, and then the question is, when you augment the litmus tests with these extra instructions, how easy is it then to run the PipeCheck with enumerating this increased litmus test? And this is also, I think, a challenge that you'll probably be facing in a real-world application.
Yeah, so that is true. So I think what would have to happen in that case is that whatever guarantees that you would be expecting to make for a particular stage that would somehow depend on the fact that you're not overflowing your store buffer, reaching this corner case or something, somehow that would have to translate into the fact that you can't actually prove that the microarchitecture level specification that you wrote down for that particular stage is actually correct in the general sense, because there might be this corner case. And so that again gets back to this previous question that if we had some better way to get from, say, RTL up to microarchitecture, then that would hopefully catch cases like that. But yeah, at this point, it is just a manual process that we keep iterating until we get closer and closer.
Well, yeah, decomposing would be an interesting idea. Sort of, yeah.
Do these designs tend to be hardened where there's some like manually written RTL in there already, or does it make more sense to look at some artifact that was, created in the process of designing? I mean, suppose you're on the inside of the design house. Right? Are the models that you write anything similar to any of the documents or models that are used in the production of the chip itself?
Yeah, so again, that's something we're hoping that the more we talk to industry, that the more they may be willing to release at least some details about how that process works. But in a general sense, I think it would be useful even, so like you said, before having RTL, then just figuring out what kind of microarchitecture you want to build in the first place. You could first write down a model like this. Maybe you have some internal design. I've talked to some people at TI that have mentioned they do have something like this, and I'm sure other companies do as well, that you have some model of what you want to happen at the microarchitecture, and then once you figure out how that works and verify that that's correct, then you can go about verifying or building each of the individual stages and then back to verifying that they do what they say they should be doing.
What was the reaction of your hosts at Intel?
I'm sorry?
What was the reaction of your hosts at Intel?
So the team I was working with was more of a research team, so they were excited by this kind of research. They were not so embarrassed, I guess, about having bugs be found because they weren't the people that were making the bugs or that produced the bugs in the first place. So from everyone that I interacted with so far, this is a positive step, I think, to making this, helping us avoid these kinds of bugs in the future. It's not really, we haven't talked to the people that built transactional memory and had the bugs yet, so I don't know what their reaction would be, but hopefully it would be the same thing, that hopefully they would be appreciating the effort.
Did you talk to their validation people? So I know they have some tools already that allege to check simulation traces against TSO.
Yeah, so there have been plenty of efforts for testing-based approaches, and so we haven't talked to them directly, but we see this as augmenting this. Like I said before, that we don't want to replace testing. You still have to do testing as much as you can to verify that it works properly, but this is hopefully something that augments that testing with a little bit more of a zoomed-in picture of what's going on.
I suggest we stop here, but Dan is around for the whole week, so if you want to talk to him, let me know.
Yep.